Hey guys, it's me, Miss Miller, here to start Chapter 5, Section 2, Right Triangle Trigonometry. In this video, we're going to remind ourselves about the Pythagorean Theorem, 6 trig functions. Now we know, most of us know all 3, which are our sine, cosine, and tangent, and then we're going to introduce 3 more. And then also looking at special right triangles and how they apply to the trigonometric system. So, let's get started. Our Pythagorean theorem refers to our right triangles, and it's allowing us to calculate either our hypotenuse or one of the legs of the right triangle with our a squared plus b squared equaling c squared. We can use this to, again, find our hypotenuse, or we can use it to identify one of the legs, and I will show you with an example. So it's important to identify that our hypotenuse is always opposite of our 90 degrees. So here my hypotenuse is 5. We're going to try to find the third side in simplest radical form. And our other side is 1. So we're missing a leg. So we need to first write down our Pythagorean theorem, a squared plus b squared equaling c squared. Then identifying that we're going to plug in 5 for our hypotenuse and 1 for b. You could plug it in for a, it doesn't matter. Then we'll evaluate and solve. So we get a squared plus 1 equals 25. Subtracting 1 to both sides gives us that a squared is 24. Now that is not what a is. We have to then take the square root. Now in the past we would have used plus or minus to find both of the square roots. However, since we're looking for a side of a figure, we know it has to be positive. So we're going to use our prime root. So it'll be positive square root of 24, which is not simplest radical form. What we want to do is make sure we simplify this by identifying the perfect square that goes into 24, which is 4 times 6. So the square root of 4 times the square root of 6 gives us 2 root 6. And that would be the side length that is missing. You could attach the word units to it, but since they didn't identify 5 as a certain measurement of inches, you can just leave it as 2 root 6. It's important to know our Pythagorean theorem when we identify our trig functions. So here again we have a triangle. Again, the longest side opposite my 90 degrees is my hypotenuse. And then we have 3 angles within a triangle. We don't really use 90 degrees here. What we are going to focus on is our interior angle, and we're first identifying this as theta. You could also have another angle, beta, up here at the top, but if we just look at this theta, we have our opposite sides opposite the angle, what's adjacent to the angle, and what is the hypotenuse of the triangle. So these first 3, I know most of us know already, is sine, cosine, and tangent. It's important to know that those words are sine, cosine, and tangent. The abbreviation is sin, cos, and tan, but we don't ever say it like that. We say the sine of theta, the cosine of theta, or the tangent of theta. Now, a lot of us know the ratio based on our acronym SOHCAHTOA. SOHCAHTOA. And all that means is that for the sine, we have our opposite over hypotenuse. So the sine of an angle is going to give us the opposite over the hypotenuse. For cosine, we have our adjacent side over our hypotenuse. And tangent is our opposite over adjacent. Now these are our new trig functions for most of us. We have secant, cosecant, and cotangent. Now, these all have a relation similar to sine, cosine, and tangent. We don't have an acronym like SOHCAHTOA. You could probably creatively make one. But when we look at secant, its relationship is the hypotenuse over adjacent. What function do you think that has a relationship with? You're right. Secant and cosine have a relationship. Notice they are inverses or reciprocal identities, right, to each other. If we look at cosecant, we're now dealing with our hypotenuse over the opposite. So it's just a ratio difference. Instead of saying opposite over hypotenuse, which normally would have been our sine function, we're doing cosecant. And lastly, our cotangent is kind of the easiest one for people to remember because cotangent is adjacent over opposite, which is the reciprocal of our tangent. So let's apply this. When we look to find all 6 trig functions for theta, and theta has gone missing, so I'll put it in here. This is where we wanted theta to be. We first need to know all 3 sides of the triangle. Right now I have 6 and 5, 6 being my hypotenuse, so I'm going to do 6 squared equals 5 squared plus b squared. We'll switch it up. So I get 36 equals 25 plus b squared. Subtract 25 from both sides, and I get 11 equals b squared. So my side AC is going to be the square root of 11, and we're going to leave it exactly as that. We're not going to round because they're telling us to leave it exact, so I'm going to leave it as square root of 11. Now I can use that information to find all 6 trig functions. So let's first start off with the sine. Now you could say the sine of A here, but instead we're going to use theta because that's what's given to us, and that's what they're asking for. So for the sine of theta, sine is again our opposite over hypotenuse. So in this case, for sine of theta, we are going to write our ratio. Sorry, my pen isn't working correctly. And we're going to have 5 over 6. Okay, good. Our next trig function is cosine. Now, you can do this in any order. I just tend to go sine, cosine, tangent, cosecant, secant, cotangent. It doesn't matter. But our cosine of theta is our adjacent side. So our adjacent side to theta is a square root of 11 over our hypotenuse, 6. And tangent of theta. Notice I'm saying tangent and not tan. And we are going to take then our opposite over the adjacent side. So again, opposite over adjacent. So we cannot leave 5 over the square root of 11. So I'm going to simplify that by rationalizing my denominator, multiplying by the square root of 11 to both sides. So I get 5 root 11 over 11. And now, again, we want all 6 trig functions. So the next thing I'm going to do, I'm going to switch up from the previous slide. I'm going to do my cosecant. And the reason is I want you to see the relationship between sine and cosecant. So cosecant, if we look, I'm going to go back for a second. Cosecant is our hypotenuse over opposite. So for hypotenuse over opposite, opposite being 5, hypotenuse being 6, so I now have 6 over 5. If I do the secant of theta, I then will have my hypotenuse 6 over my adjacent side. And again, I'm going to have to simplify this to then give me 6 root 11 over 11. And last but not least, let's find the cotangent. I wrote cosine. Cotangent of theta. And cotangent of theta is now going to be square root of 11 over 5. And if you notice, you can see the relationship. If sine is 5 over 6, then cosecant is 6 over 5. If cosine is the square root of 11 over 6, then secant technically is 6 over root 11, but we know we have to rationalize. Same with tangent. Tangent was originally 5 over root 11, so cotangent is root 11 over 5. Remember to always rationalize the denominator if possible. As we just said, here are our reciprocal identities. The next video we're going to talk more about these identities and how to apply them. but to understand that sine and cosecant are our reciprocal identities. So again, if we take the reciprocal of sine, we'll get cosecant. The reciprocal of cosecant is sine. Same with cosine. The reciprocal of secant is cosine. The reciprocal of cosine is secant. If we take a look, the reciprocal of cotangent is tangent, and the reciprocal of tangent is cotangent. Just cementing more the idea that when you ever have these identities, know their relationships. So sine, cosecant, cosine, secant, tangent, cotangent. You know I'm all about my weird ways of remembering things. So for cosine, it starts with a C and ends with an S. For secant, it starts with an S and ends with a C. That's how I remembered it in high school. And for cosecant, S is in the middle and it starts with an S. It might not help you to remember, but it helped me remember in high school, so I figured I'd share. And cotangent and tangent is a little bit easier since they're so similar in their names. All right, last topic I want to talk to us about is special angles. That deals with our special right triangle. So I gave us first our special right triangle of a 30, 60, 90 triangle. We know that 30, 60, 90s follow this format, that it's just a proportion. So the opposite of 30 degrees is 1 unit. You can also think of this as x. This is root 3x and 2x. So whatever is opposite my 30 degrees is a multiple. It always follows this special ratio. So if we dive first into using 30 degrees as my theta. So I'll put a theta right here. 30 degrees. And sine. Again, sine is our opposite over hypotenuse. So the sine of theta for 30 degrees is going to be 1/2. And that's always, no matter what triangle is drawn, it will simplify to be 1/2. So now if we take a look, the cosine of 30 degrees, or pi over 6 radians, so the cosine of 30 degrees, or pi over 6 radians, is going to be my adjacent, which is root 3, over my hypotenuse. And my tangent for this angle is going to be root 3 over 3. And you might be asking, how did I get root 3 over 3? Well, remember, your tangent is your opposite over adjacent. So that would have been originally 1 over root 3. And we know we have to rationalize that. So if you multiply by root 3 to both the top and the bottom, we're going to get root 3 over 3 for my final answer. All right, cosecant and sine have a relationship. What's that relationship? They're reciprocal identities. So you know that cosecant is your hypotenuse over the opposite side. So that would be 2 over 1 or 2. Or if you just know what sine is, it's the reciprocal too. Secant of theta, again, secant of theta is now going to be my hypotenuse over my adjacent side, which would be 2 over root 3. We cannot leave like that. We have to rationalize, multiplying by square root of 3 to both the numerator and the denominator, and we'll get to root 3 over 3. And my cotangent, I want you to look back at the tangent. Tangent was 1 over root 3. So the reciprocal of that is just root 3. Also looking at your triangle, cotangent is now going to be your adjacent over your opposite, which gives us root 3 over 1. All right, still working with this triangle, I'm going to have us go down to 60 degrees for theta, or pi over 3 radians, right? We've worked a little bit with transforming from degrees to radians. Pi over 3 radians is 60 degrees. So using that, let's see what relationship we have. 60 degrees, we're going to use our opposite over hypotenuse, which will then give us root 3 over 2. Cosine of theta is going to be my adjacent over my hypotenuse, which will be 1/2. If you take a look here, sine and cosine have a weird relationship, and it's actually not that weird because 60 and 30 are complementary angles, and sine and cosine, we're going to see more of those relationships later, and with a complement angle, what those equal. But notice that the cosine ended up being the same answer for sine of 30, and the sine was the same answer of cosine of 30. All right, your tangent now is going to be your opposite over adjacent, which is going to give us just root 3 over 1, also known as root 3. Cosecant, we're going to find by taking the hypotenuse over the opposite. So again, we're going to have 2 over root 3, which we cannot leave, so we're going to end up getting 2 root 3 over 3. Secant is going to be your hypotenuse over adjacent, so here we'll have 2 over 1, which just is going to equal 2. And cotangent of theta is now going to be 1 over root 3, which again we're going to rationalize to be root 3 over 3. All right, so that is our 30 and 60 special angles. Our other special angle is 45. Now 45-degree triangles are 45-degree right triangles are isosceles triangles because they have the same measurement. The complement of 45 is also 45. So it doesn't matter here if we look at this angle as theta or this angle as theta, as long as we're looking at 45 degrees, because if my one side is 1 unit, my hypotenuse is going to be square root of 2. Again, you can think of this as x root 2 times x, whatever this is. So if this is 3, then this would be 3, and this would be 3 root 2. That pattern I know you guys learned in geometry. So let's take a look at looking at 45 degrees or pi over 4 radians. If we take a look at our sine, we'll get 1 over root 2, which we know we cannot leave. So we're then going to get root 2 over 2. And since it's in the isosceles triangle, they'll be the same answer for cosine. And then tangent is pretty easy because we'll get 1 over 1, which is 1. Now looking at cosecant, we're now going to take our hypotenuse over the opposite side. So root 2 over 1, which is just root 2, which will be the same answer for secant because, again, this is an isosceles triangle. And then cotangent for 45 degrees is 1. It's pretty nice that way. So this is a lot of information to give you at once, and we'll be working with 30, 45, and 60 a lot this chapter, and eventually this will be memorized. But if you ever get stuck, you can always draw the triangles to help you, as long as you remember what a 30, 60, 90 triangle looks like and what a 45, 45, 90 looks like, and how to find those measurements. All right, and today's assignment is on Delta Math, and in your textbook, it's just a few extra practice problems. Please submit a photo of your work, and if you need more time to do it, please let me know. I miss you all, and I'm available anytime through email to ask any questions. Have a great day, guys.